It's good to see you all again, and it's good to see that you didn't sleeping, at least most of you. Hope you enjoyed yesterday's tour, sort of tour. And again, thanks for the translator. Did a great job. All right, so now to continue with what I was talking about yesterday, the last thing I talked about was P-completion, okay? So I didn't give the definition, but I told you it was a functor, right? So I was talking about P-completion. I talked about how this was a functor from topological spaces to topological spaces. That came also with a natural transformation from the identity to the P-completion. That is, we always have a map from each x, from x to its P-completion. Okay? And I also talk about some class of good spaces that behave really well with respect to this P-completion, that were the class of P-good spaces. So let me remind that definition. X is P-good if the P-completion is homotopy equivalent to the P-completion of the P-completion. It's something that we would like to have, but doesn't always happen. And I also gave you a theorem that told you about two classes of spaces that are P-good. So one of them was the class of simply connected spaces, and another one was the class of spaces whose homotopy groups were all finite. And this is going to be good for us because we're going to be dealing with classifying spaces. So for finite groups is one case, and for compactly groups is the simply connected case. Okay? So this is where I left off. Any questions? So this is where I left off yesterday. Now, I'm only going to be dealing with P-good spaces. So from now, I'm going to give some properties of the P-completion, but I'm going to assume that all my spaces are P-good. So from now on, assume spaces are P-good. Okay, so since I didn't define what P-completion is, I'm just going to give you the properties and ask you to believe that they hold. But hopefully some of them, Zachary will talk about them too in some detail. So some properties. So one, if f from x to y induces an isomorphism in cohomology with coefficients in Fp in the field with P elements, then there is a unique map up to homotopy from the P-completion to Y such that the following diagram commutes up to homotopy, such that the diagram commutes up to homotopy. And the diagram is I have X, I have the P-completion, I have my map from X to Y, and then there is a unique map here up to homotopy such that this commutes up to homotopy. Okay? That's the one that should go the other way. Thanks. Still too early. Okay. So we can think of the map from X to its P-completion like a final object in the category of maps that induce isomorphisms in the cohomology mode P up to homotopy. Okay. Now, another relationship between the P-completion and the FP cohomology, and to me is really the most interesting and the one that really tells me, makes me understand what the P-completion is about, is that the P-completion, what it does is it transforms homology isomorphisms into homotopy equivalences. And that's something really cool. Yeah? So a map from X to Y induces an isomorphism cohomology with coefficients in Fp if and only if the P-completion is a homotopy equivalence. Okay, so this result is really strong, but it's really cool too. Now, I'm not sure here if you may need some finiteness conditions from X and Y, because usually this is stated with homology. So you may need some finiteness condition, but modulo of finiteness condition that holds. And also, this is the reason why P-completion is showing up here, because yesterday we were talking about the cohomology with Fp coefficients on classifying spaces. And we have certain decompositions that we want to lift to the P-completion. Now, it makes sense that it's possible to do that precisely because of this condition, at least heuristically. Yeah. Now, maybe some computations that we can do. So what can we know about some of the homotopy groups, for example? So if X is simply connected, the homotopy groups of the P-completion are isomorphic to the homotopy groups of X tensor with the p-adic numbers. So in this sense, is that X, the P-completion takes only the P part of X. Yeah? Of course, when it's not simply connected, this doesn't hold anymore. But this was the motivating example. When P-completion started being studied, it was studied by Sullivan, and Sullivan focused first on simply connected space. Yes?
Is the tensor over FT there?
It's the tensor over C.
Oh, okay.
Because this is an abelian group. I should say here for I greater or equal than 2. Because for I equal to 1 is 0, so the other one is also 0. And 4, what if it's not simply connected? Well, there is a case that is interesting. If all the homotopy groups of X are finite, then we can say something about the fundamental group of the P-completion. So the fundamental group of the P-completion is isomorphic to pi 1 of X modulo OP of pi 1 of X. Now, what is OP? OP is the smallest normal subgroup of index a power of P. Okay, so that's nice for computing. And well, since our spaces, we can think of spaces as being built out of Eilenberg-Mann spaces, it would be nice also to know what this construction does to Eilenberg-Mann spaces. So final property, what can we say about the homotopy groups? Well, let A be an abelian group. An abelian group. What can we say about the homotopy groups of KAN P completed when n is bigger or equal than 1? So here we also include 1, but only the case when it's an abelian group. When it's not abelian, much harder. So these homotopic groups, now this doesn't have to be an Eilenberg lane space anymore. I mean, it's going to have two homotopic groups at least. Well, one of them could be zero, but not in general. So the homotopic groups are going to be X over C of Cp infinity A if take more space. If I is equal to n, hom from Cp infinity to A if I is equal to n plus 1 and 0 otherwise. Now, does everybody know what Cp infinity is? Yes? No? Okay. There are a few yes, a few no, so let me say what it is. So Cp infinity has a few descriptions. We can think of Cp infinity as the p torsion inside the circle. See, the circle is a group, and there are elements of order p, the pth roots of unity. There are also elements of order p squared, the p squared roots of unity. So when we put them all together, that's Cp infinity. Another way to think about it is as a direct limit of all the Cpn's, the union of all the Cpn's. So you have Cp sits inside Cp squared sits inside Cp cubed, and so on. So the direct limit of that. And if you want something more concrete, you can also express this as Q quotient by C1 over P. 3 equivalent descriptions. It's a fun exercise to see that they are all equivalent. So have at it. Also, it's good to find an example where really the P completion of an Eilenberg lane is not an Eilenberg lane. But I think it's also fun to figure out what the completion, the P completion of this space is. So I'll let you as an exercise to figure out what this is, and the answer is quite surprising. Okay, so next, let me now go to the P completion of classifying spaces. So let me do a few examples that are going to be, I'm going to illustrate that the P completion really behaves well with respect to the structure of the group as well. So first example, say that Q is a P prime group. Now by P prime group, I mean that the order P does not divide the order of Q. Well, in this case, it's really simple to see that BQ, P completed, is, anybody want to take a guess? If you don't have any P information, what should you get? It should be contractible. And it is contractible. Right? And that really comes from here. Right? Because from group cohomology, we know that the cohomology of a group which doesn't have P torsion is 0. Well, it's a cyclic, to be more precise. So it has the same cohomology as the point, so it's a homotopy equivalence. Yes?
I'm a little confused. Are we using these 5 properties as definition of P completion?
Not as definition. I mean,
How should I think of what the P completion is?
So I'm not giving the definition, I'm just giving properties that I'm going to use. The definition will be given later. But you have to think of the P completion as taking the P part of a space, like breaking your space into one part for each prime. Up to homotopy, yeah. there is some results later that tell you that when you have all your p-completions, well, let's assume that X is simply connected, just to make it simpler. When you have all your p-completions for all the primes, and when you have the rationalization of a space, which is something similar, but say on the homotopy groups you rationalize, you can recover your space up to homotopy from this diagram, as the homotopy pullback of this diagram when you have certain finiteness conditions. So what you are doing is like separating your X into different pieces, one for each prime, one for the prime 0, if you would like, for the rationals, and then put it together, you recover your space X up to homotopy. Now the construction of XP is long, it's complicated, that's why I'm not giving it, but there will be a talk about it later on. So I'm just going to use the properties that I'm stating, that's why, yeah. Yes?
Can you say a little bit about how you get this for the homotopy groups?
Which one? This one?
Yeah.
Maybe I can tell you later.
Okay.
Because, yeah. Because that will take me off track for a while. So.
Okay. I guess I was just wondering, like, do you use a spectral sequence or?
No, it's not that. It's not that hard. You don't need spectral sequence for it. Yeah, I can let you know later how it goes more or less. Any more questions? Okay, so this is what the p-completion does to a p-prime group. So the p-completion doesn't see, in a way, p-prime groups. Now let's see what it does to p groups. It should be almost the opposite. So 2. Well, something that comes from 5 is that if I do the p-completion of BCP, this is again BCP. Okay? So we will only need to check that home of CP infinity CP is 0, and this is CP again. So an exercise in algebra. But the reason why I'm saying this specifically is because it's going to help me in the general case of P groups, general P groups. So now if P is a P group, there are some properties of group theory that tells you that every P group has a normal subgroups of index P. Okay? It has a normal subgroup of index P. Well, let's call it P1. Well, that means that we're going to have a long exact and short exact sequence of groups of this form. Yeah. And a short exact sequence of groups gives you a fibration of the classifying spaces. Okay? And now, there is another property that I didn't state, because I didn't want to say too many, that when you p-complete something, and the first one remains fixed, then the we can sort of p-complete the fibration. So there is a fibration like this. So now, how will we prove that BP, P completed, is again BP, is homotopy equivalent to BP by induction? If we assume that for all subgroups of a certain order is true, then this will be again BP1, right? And then I use the long exact sequence in homotopy groups, and that will tell me that this is an Eilenberg-Marlens space. And then I compute my pi 1, my fundamental group, using that property. Does the process look fine? Yeah? Yeah? Well, let me just write what I said in words. Use induction on the order of P. The long exact sequence homotopy groups and compute pi 1. Using this. In that case, the smallest normal subgroup of index of power of P is going to be 1. Okay, so therefore, BP be completed is homotopy equivalent to BP. Okay, so that's nice. Now, once your groups are not P prime groups or P groups, then the issue becomes much harder. Right? I mean, sometimes it's not that hard, so let me give you an example. For example, you take sigma 3, and you P completed at 2. This is homotopy equivalent to BC2. So that's kind of a simple case. But even for the same group, now if I take, the prime 2. But now if I P completed at the prime 3, this is much harder, right? And this can be seen. I mean, it's not an Eilenberg-Marlane space anymore. So, it's a symmetric group with 3 elements. Sorry, of the symmetric group with 6 elements. The automorphisms of a set with 3 elements. Actually, the classifying space of that, the P-completion of that, yes. You can see that it fits into a 5 ratio. I'm not going to prove that, just to give you an idea. It's much more complicated. Map J, where here J is a map of degree 3. And S3 has homotopy groups in not only in degree 3. Well, degree 1 has nothing, but has many homotopy groups. So you're not going to have different homotopy groups for this one too, not only in degree 1 or. Anyway, this is just to say that this is a hard problem, to know what the homotopy type of BG completed at P is. Okay. So now going back, so this is just a small introduction to a P completion. Now going back to fusion, something that I would like to talk about today is the idea of why the Martino-Pridy conjecture is true. Yeah? So kind of the whole lecture is going to be, well, the motivation for the proof and a sketch of the proof. So remember, the Martino-Pridy conjecture said that BGP was homotopy equivalent to BG prime P if and only if we have an isomorphism from S to S prime, from the CILO subgroup of 1 to the P CILO of the other, that induces an isomorphism of categories from the fusion system of G to the fusion system of G prime.
What is FS?
And this is the fusion system. This is the category whose objects are the subgroups of S, of the Silo subgroup, and the morphisms are conjugations by G conjugations. Okay. Yeah, so we introduced that yesterday. So now, what is the hard part here? What is the easy part? The easy part is this direction. Okay? And the hard part that uses the classification of finite simple group is the other one. So most of my talk is going to talk about this direction, but I also say how the other one goes. Okay, so I would like to talk about fusion, a bit more about fusion, but I need to do a little recess to talk about homotopical limits. Okay. Let me talk a bit about homotopical limits. All right, so we all know what a co-limit is in the topological category. I mean, Mike has used it a couple of times in his talks or more. So I guess the case that we have seen more is we have a map from A to X and a map from A to Y. The co-limit of this is, so the co-limit is X disjoint union Y quotient by an equivalence relation, that the image of A in Y is the same as the image of A in X. So we want our A to be the same in X that in Y. I mean, we don't want to have two copies of A. We want to have only one, right? Now, if you consider these two inclusions, yeah, what this is saying is that the composition going this way and the composition going that way, they are equal, exactly equal. Now, the homotopical limit aims to mimic this construction up to homotopy, right? So let me give you a picture. If I have my X here, and I have my Y here, and my space A over here, now my functions are going to give me, well, it's going to send A to this piece over here. It's going to send A to this smallest piece over here. So the co-limit will be gluing X and Y together and identifying these two. These will be the only parts that are glued. The homotopical limit, on the other hand, what it wants to do is that these two inclusions, I don't want them to be equal. I want them to be homotopic. Okay? So what I want to do is, instead of gluing it directly, I put a cylinder here, and I put a cylinder over there. And that will be the homotopical limit of this diagram. Okay? Now, I want to have homotopical limits that are a bit more complicated than this one. Okay? But they're going to be much complicated than that one. So in general, what I would like to do is to define, given a functor, F from a category to topological spaces, I want to have a definition of the homotopical limit of this functor over the category C. Now, the co-limit, again, will be the same. I mean, whenever we have a map in the category, I want to sort of identify, have an identification between the image. So if I have a map from, say, C1 to C2, yeah, then this is going to give me a map of spaces from the image, right? Sort of like here, right? So I want to identify them if it was only the colimit. But because it's the homotopical limit, every time I have an arrow, I want to put a cylinder like that. Yeah? But this situation is kind of too simple to see what's really going on, because here we don't have compositions of arrows. I mean, this is the category in this case will be just this one. Well, and the identities, but it really has only two arrows. Right? Now, what happens when we can compose more than two arrows? Okay? Then not only we want to put cylinders, but every time we have a double composition, we want to put a homotopy between the two cylinders too. Every time we have a triple composition, we want to put a homotopy between the other homotopies, and so on. It's sort of like the geometric realization. And if you see the description for that, which can be given, it's not that hard to give. So one model for this can be given as follows. So remember, Cn is the set of n composable arrows. So this is sigma 0, well, maybe I should put sigma 1, sigma n. Then this will be f of sigma 0 cross delta n. And then quotient by relationships. Now, what relationships are these going to be? Well, when I take the boundary, right? I take the boundary, I'm going to identify with the other one. Yeah? So I don't want to write them explicitly because it takes a while. What is f of 0? Oh, sorry. For some reason I had sigma 0 at the beginning and sigma 1. So sigma 1 is a, oh, and now I know why I had sigma 0. Sorry. So let me go back. This doesn't make sense. So sigma is a, yeah, sorry, I lost it. So sigma is a set, sorry, Cn is a set of n composable arrows, okay? So this can be given as an arrow here, say alpha 1, alpha 2, alpha n, okay? So these are objects of the category, sigma 0, sigma 1, now I know why, sigma 2, sigma n, okay? So what I'm going to do is I'm going to apply the functor only to the first object. That's going to give me a topological space. This is the one I want to put there. Sorry about that. Anyway, this homotopical limit can be a hard object to understand. But later on, I'm going to give you a different construction of this, which is much nicer, and is going to be given as the geometric realization of a category. So that's also why I don't want to get into much details about that. Okay? So now, why am I interested in homotopical limits? Now, one way that people try to understand these spaces is by trying to decompose them, into homotopical limits in such a way that each of the pieces was the classifying space of a group 2. Right? So this is usually called homological decompositions. So work in homological decompositions, and if I had to mention somebody, which really, I mean, some paper that is important for this, a paper by Dwyer in '97, that is called something like homological decomposition. Yes?
Yeah, so the identification there, is that where you take a chain of these things and identify it with its corresponding simplex, or what?
Yeah, so I mean, you identify this part with the boundary of n minus 1 by going to the n minus 1 part of this. So if I go to the face corresponding to the part I will take out the I, or no, I will compose it.
Okay.
It's like the same identification where you construct the telescope
Yes,
of a space, right?
right. So the homotopical, in the mapping telescope is a particular case of the homotopical limit, where the category that you are using is this one. That one. So yeah, it's the same identifications. Yeah. I know that this can be a bit hard to understand at the beginning, but I'm not going to use much about this construction. I'm going to give an alternative construction, and that's the one that I would like. So, like I was saying, working homological decompositions showed that BG completed at P is homotopy equivalent to the homotopical limit over the fusion system of factor J given by I take a group Q, I take it to centralizer P completed. Okay? So if you want to see it in a more informal way, let's write it this way. Okay? And this kind of is going to justify why the centralizers are going to come up. Now, oh, sorry, I'm missing, I'm missing a P completion here.
What is it?
Huh?
What is S?
Oh, S is a P silo subgroup of G.
The same P.
Yeah, the same. Yes.
So I'm guessing the fusion system will always be like a small category.
Well, yeah, because I mean, G is a finite group, so it has a finite number of subgroups, and conjugations are quotients of a normalizer. So G is a finite, so at most you have a finite number of elements.
Okay.
Yeah. It's even finite, yeah. I mean, later on, we're going to go to different groups where it's not really finite, but it's still small, still a set. That's going to be interesting too. Okay, so now what we say, does this statement help me understand a bit more BGP completed? Well, sort of. I mean, so the composition, I mean, if you could compute the P completions of that, and you knew all the maps and everything, then maybe. But this is still quite hard. Right? I mean, we're still reducing the problems to doing it for many subgroups. It's still quite hard. So now, what we can do is to try to, instead of looking at all the subgroups in the fusion systems, trying to look at the subgroups for which this is simpler. Yeah? That's the idea. So that motivates the following definition. Definition, a P subgroup Q of G is P-centric if the centralizer in G of Q is equal to its center cross OP of CG. So remember, OP was the smallest normal subgroup of index power of P. In particular, this has order prime to P.
But what was CGQ?
Oh, it's the centralizer of Q. So it's the elements of G such that GQ is equal to QG for all Q in Q. Yes.
So when you say, excuse me, prime to P, you're not including 1, because, oh, that could be trivial, right?
It could be trivial. I'm including that case too.
Actually see it.
Yes.
Yeah.
Yeah, I'm including that case too. And just to have the notation a bit simpler, let me call this the composition Cg prime of Q. So this part I'm going to call it Cg prime of Q from now on, just to make it a bit shorter. Now, what's good about this? Well, what's good about this is that BCG of Q is now the product of this. And since I'm doing the P completion of that is going to be only the P completion of that, because this has order prime to P.
So Z of Q is also the centralizer of Q?
Oh, sorry, I didn't define what C of Q is. I'm so used to the notation that I, for some reason, I think that everybody knows it, but no, C of Q is the center of Q. So sorry, let me tell you what that is. C of Q are the elements of Q that commute with all the elements of Q. So of course this is included in the centralizer, but in general it's different. All right, so what this decomposition is telling me now is that B, C, G of P, P completed at P, is homotopy equivalent to B, C, P. Okay? Now, well, we'll have to say completed at P, right? Let me do that. But, oh, I was using Q, sorry. We'll have to say P completed, but CQ is a subgroup of Q, and Q is a P group, so this is also a P group, and we saw that this is BCQ. Yes? So in a way, we made it simpler, right? Now we could say that BGP is homotopy equivalent to the homotopical limit of FSG of BCQs, and all P completed at P. Okay, a bit simpler, but this is still not completely combinatorial. We would like to have a combinatorial description. And what do I mean by combinatorial? I would like my BG completed at P to be the geometric realization of a category and then completed at P. I mean, I would like the whole inside to be combinatorial in that sense. Yeah. Now, how do I do that? Now, to do that is when I need my alternative construction of this homotopical limit. So I need to talk about the Grothendieck construction. All right, so the Grothendieck construction starts as follows. I have a category C, and I have a functor from C to cat, the category of small categories. Okay? Yes?
So that last equivalence,
Uh-huh.
is that only if you're lucky enough to have this happen for every?
Oh. Okay, that's, yes. Let me put that on hold. I forgot to make, of course, this is only true for the ones that are, yes.
But that's like the dream case.
Yeah, just let's say that that's a dream case, but I forgot to say a few things that are important. Yes, so I was going too fast. Okay, so when Q is F-centric, is P-centric, this happens. So we would really like to concentrate, like Zachary says, on the simpler case, what this is always true. But of course, not all subgroups of G, not all P subgroups of B are going to be P-centric. Right? But there is a theorem Alperin fusion theorem. Well, actually, what I'm going to give you is not the full statement of Alperin fusion system, but more of a corollary of the theorem. Says that the category, well, the morphisms in the fusion category are generated by automorphisms of P-centric subgroups and inclusions. Okay? So even though in the category we have subgroups that are not P-centric, every morphism factors through P-centric subgroups. So if I have a map P1 to P2, and these are not P-centric, what it is true though is that, well, we have a map, a G conjugation. What is true is that we can fit P1 inside a P-centric group, Q1, then do an automorphism here, that is a G conjugation. Then there's going to be another group here, let's call it R1, that is included in here, and such that the image falls inside here. Then another inclusion, and so on, until we get to there. So in some sense, the morphisms that we care about are just but those, automorphisms of P-centric subgroups and inclusions. So really, when we do the homotopical limit, we don't care about the rest of subgroups, we only care about the P-centric. It's going to give us the same result. So let FSGC be the full subcategory of Fs of G whose objects are centric subgroups. P-centric subgroups. Okay, and now with this and Alperin's fusion theorem, now I can make the true statement. So now, true statement is that BG P completed is the P completion of the homotopical limit over the fusion category of centric subgroups B CQ. Okay, now this makes sense. All right. But, I mean, still the same thing happens as before. I mean, the whole inside is not combinatorial. So I still want to have it as the realization of a category. Okay. Is this okay now? It's just the stage fright. You know, we have a camera on the front. Yes. Anyway, so like I was saying, now I want to talk about the growth and deconstruction. So let me go back to that. Now, this was a fantastic idea, the growth and deconstruction. And it goes as follows. I have a category C, and I have a functor from C to the category of small categories. That is, for each object of C, I get a category. For each morphism, I get a functor between those categories. Okay? And I'm going to assume that my functor is contravariant. I mean, you could also do it with covariant, but that my functor J here is contravariant, right? I mean, if we have a map from Q to P, that gives us a map from the centralizer of P to the centralizer of Q, right? So I want to do it in the contravariant case just because that's what I'm dealing with now. Now, I'm going to define the Grothendieck construction. So the Grothendieck construction is the category C semi-direct product F. That's just a notation. Whose objects so the objects of this category are pairs A, X, where A is an object in the original category C, and X is an object in the category F of A. Okay, let that sink in for a while. And now morphisms. I want to see what the morphisms are for from AX to BY, let's say. So my morphisms are going to be pairs. Are going to be pairs F, H, where, let me tell you where each of them is. So F is going to be just a morphism in C, from A to B. It's a morphism in the original category. Yeah? Now, a morphism in C, when I apply the functor, is going to give me a functor. Right? This is going to give me a functor from F of B to F of A. This is a functor. Yeah? And Y is an object in F of B. So I can take the image and consider F of Y. It's going to be now an object of the category F of A. It's a bit confusing, all the categories and functors, but. So my H is just going to be a morphism from X to F of Y in F of A. A morphism here. Okay, this is a strange construction, right? You say, well, I had something really hard and now it seems like I'm doing something even harder, right? But this actually simplifies things, believe it or not. Okay, so why is the Grothendieck construction useful? The Grothendieck construction is useful because of a theorem by Thomason. That relates the homotopical limit with the realization of the Grothendieck construction. So think of this functor. Right? One thing we can do is compose this functor with the geometric realization. And that will give me a map from, well, a functor from C to the category of topological spaces. So let me call that one. So if I have C to cat, this is a functor, and then I take geometric realization. This is also a functor. I'm going to call this composition as the realization of F. Then the theorem by Thomason says the following. The homotopical limit over the category C of this functor, now homotopical limit of spaces, yeah, is homotopy equivalent to the geometry realization of this category. All right? So that's how we go from homotopical limit, something hard, to geometry realization of a category, principle easy, although the category is kind of hard now. But it's more combinatorial. We are making progress. And you have to be a bit patient. Okay, so now we would like to apply that to this. Yeah? So to apply that to that, we would like to find a functor from F from the fusion system to categories such that the geometry realization is BC. Now, yeah. All right, so one thing that we could do is the following. We could say that BGP is homotopy equivalent to the geometric realization of FSG BC P completed at P. Right? So where this BC is the functor from FSG into categories that to each object here, to each subgroup, gives me the category BCQ. This is contravariant functor. And remember that this is the category with one object, and the morphisms are CQ. So this is something that we could do. I mean, and check that that will hold, right? But actually, even though this gives you a combinatorial description, it's not the best that we can get. We can get something better. Okay? So instead of taking these categories, there are other categories with geometric realizations is also BC of Q. And we're going to choose one that is a bit harder, but that's simplified. This one, I guess you could also simplify to the other one, but it will take much work. So what is the alternative? And let me warn you that the alternative looks ugly. For 5 minutes, then it looks nice. So the alternative is the following. So the alternative is the following. For each Q, we are going to construct a category. Consider the category R of Q, which is defined as follows. The objects are functors from BQ to BG. I should probably write what I say. That are G conjugate to the inclusion. Okay? So, I mean, a functor from BQ to BG is just a group homomorphism from Q to G. Right? So to say that a functor from there to there is conjugate to the inclusion is just the same thing to say that I have a G conjugation from Q into G. It's simpler maybe. And the morphisms, and this is a bit hard to describe, are the P primary part of natural transformations. I should probably explain what that means. When you look at the category whose objects are these, but the morphisms are all natural transformations, you can check that what you get is actually a groupoid. Every map is an isomorphism. Yeah? Now, when you have, and actually it's a connected groupoid. Every two objects are connected by a morphism. So when you have a connected groupoid, right, and you have your group of automorphisms here, and these are connected by morphisms, one can check that the automorphism groups of every object have to be isomorphic. So this automorphism group is also going to be G. Yeah? So there is a process that from a groupoid, from a connected groupoid, gives you another groupoid whose morphisms are the P primary part of these groups. And that somehow fixes these arrows in the middle so that everything makes sense too. So this is a process that can be done. It's an easy, it's a fun exercise to do, not that difficult. But, I mean, this category doesn't tell you much. So let me give you an equivalent description that doesn't need to use these P primary parts. So this category, this category is isomorphic. To the category whose objects are, now the description is going to be a bit more down to earth. Every map here is a conjugation, so we can just look at the image. Right? The objects are just the conjugates of Q. Mm-hmm. And the morphisms, so let me, and the morphisms from G, Q, G minus 1 to K, Q, K minus 1 are the elements of G such that S minus 1 G, Q, G minus 1 S is equal to K, Q, K minus 1 for all Q in Q. This is sort of, I mean, this S is sort of like an element that centralizes a subgroup in another. I mean, it's not just normalizes this subgroup in this one, but it's object, I mean, it's element by element. Okay? And also, I want that S minus 1 G, Q minus 1, that if you think about it, if you pass the Q and the K minus 1 to this side, and the K minus 1 to this side, it will give you that this element is part of the centralizer of Q. But I don't want to take the whole centralizer. I want to take the P primary part, which in this case is their centric, corresponds just to the center. Okay, a bit complicated, right? But if you think about it as a groupoid, it's a groupoid where the objects are G, Q, G minus 1, K, Q, K minus 1. There's a bunch of arrows in here. But what you get in here really is just the centralizer of G, Q, G minus 1. And what you get in here is the centralizer of, the center of G, of this. Now these two centers are isomorphic to each other, and they are all isomorphic to CQ. So it's a groupoid where the G's are CQ. Right? Now, for an exercise that I wrote yesterday on the board, a connected groupoid is always isomorphic to the category has one object and just the automorphisms of the group. So, no, sorry, not isomorphic, equivalent. That's different. So actually, RQ is equivalent to B, C. Okay? So instead of using this, I want to use R. Okay? Now, why do I want to do that? But okay, so for a moment, this is true. So let's start with that. This is homotopy equivalent to the geometric realization of this R be completed. But now it's really easy to see that this category is equivalent to one that is very algebraic. And that's why I wanted to do this. So now it's easy to check that the category FSCGR is equivalent to the category LSCG. Sorry about the notation, I know it's a bit annoying, all those symbols, but whose objects are again P-centric subgroups of S. I mean, it has the same objects as this category only, the fusion system centric. And the morphisms, and here's the funny part, morphisms from Q to R is the normalizer from Q to R quotient by CG prime of Q. Yes?
So you defined R as a category, so when you're semi-direct producting whatever with that over there, you're taking R to be the functor that goes from the category FSCG to cat.
To cat.
And, okay, but it is the centric one, it's being restricted to the P-centric ones. You have the little upper C there.
Yeah, so this is, so what she's saying is that I only define R of Q. So what I mean here by R is really the functor from FSG to categories that takes my Q to R of Q.
So I guess what I'm asking is, should there be a little upper C on that FSG or no?
Yes.
Okay.
Sorry, it's just missing all my C's. Yeah. Okay, so now this category is much more algebraic, and in fact, it's very similar to the fusion category. The fusion category, the morphisms were given by normalizers, quotient by centralizers. Here, we don't quotient by the whole centralizer, just the P prime part. Nice, no? But also, this equivalence has the following property. So, do I still have the Grothendieck construction? No. Well, remember the Grothendieck construction, the objects were given by two components, okay? Where the first component was an object of C. So if I look at my Grothendieck construction, I always have a functor that sort of forgets the second component. Yeah? And in the first component, the morphisms were just morphisms in C. So this makes sense. Yeah? Now, this equivalent is actually compatible with this projection in the following sense. If I take FSG centric semi-direct product with R, I have a projection here to the fusion system. On the other hand, I also have an equivalence from this category to that one. So this is an equivalence. Yeah? Well, the good thing about this construction is that through this equivalent, this map is really easy to understand. And this map on objects turns out just to be the identity. And on morphisms, remember on morphisms, morphisms here are things like that. While here is CG of Q. So this morphism is just quotient by the part that we are not quotienting yet, by the center of Q. And that way we get to the whole normalizer quotient decentralizer. It's a nice construction, and it's a functor that's easy to understand algebraically. That's what we want, something algebraic. Does it make sense? Yeah.
Yeah, I'm just gonna ask if you took the like over category thing you
Mhm.
did at the beginning.
Yeah.
I saw that and I thought it was really interesting, and so I'm waiting for it to show back up.
Okay.
Would that be meaningful here?
The over category here? Well, the geometry realization of this is quite different from the geometry realization of that. But if,
This is more like
huh? Sorry?
I was just kind of wondering how we should be thinking this functor. Is it more like a localization kind of functor? Or?
Is it like a localization? Well, this is like a loss of information going from there to there. So the way I think about it is, in this part, I have the algebraic part of the group, right? All the conjugation, this is completely algebraic. When I go up here, I have the topological information too, in the sense that here I already have the BG be completed is the geometric realization of that. So let me write that. I mean, what I proved is this. So I have exactly what I wanted. But yeah, I'm not sure what the fiber will tell me in this case. Maybe it's a good question. To be honest, I haven't thought about it. Okay, so I should be about ending. So let me give a name to this guy. So LSCG is called the centric linking system associated to, well, centric linking system of G with respect to S. Huh? The centric linking system.
What is the thing
Inside?
no, after centric, what is it? After centric.
Linking? Linking. Yeah, I don't know what the name comes from, but linking. Okay. So now, what do I want to say about this? Now, the point of doing this is that all my topological information will be algebraic, right? So it will be a shame now if this BGP was not determined completely by that guy. But the good thing is that it is. Otherwise, I would have spent 1 hour talking about it. So the theorem is the following theorem. BGP is homotopy equivalent to BG prime P if and only if the triple SFS CG LSCG is isomorphic to the triple S prime I have to explain what this isomorphism means. This isomorphism is an isomorphism of groups from S into S prime that induces an isomorphism of categories from the fusion system and an isomorphism of categories with this. Right? Because going that way is clear, right? Because if these two categories are equivalent, geometric realizations are going to be homotopy equivalent. So that part is clear. For the other part, I'm going to take a couple of minutes. Just for the other part, one needs to see that there is an equivalent description of the fusion system and the linking system that can be done in terms of the classifying spaces. So our description was completely algebraic, but there is a topological description that is equivalent. So let me give you the one for the fusion system. So Fs of G is equivalent to the category whose objects, sorry, I'm always forgetting the C. If there is no C, put a C. Objects are P-centric subgroups of S. And the morphisms, and this is really mind-blowing, the morphisms are given as follows. They are group homomorphisms. Yeah, remember that before there were G conjugations that satisfy the following. Satisfy that when I do BQ to BR, the induced map BF, and then I consider the inclusion into BGP. So we always have a map like that, yeah? Just the inclusion and then the completion. This diagram commutes up to homotopy. Really incredible that that could be the same thing, but it is. And there is a similar description that I'm not going to write because I'm running out of time, but I'll write it next time, that LS, the central linking system, is equivalent to the category whose objects are maps from Q to R that satisfy this, and a homotopy, well, a homotopy class of homotopies realizing this homotopy. Yeah? And the map going down will be for getting the homotopy. Now, is that good for anything? Well, what happens now if I have this equivalence? A homotopy equivalence is going to give me a map. Well, it's going to give me an equivalence of category from FSG to Fs prime G prime by composing these maps with the equivalence, and vice versa. And the same thing for the central linking system. So that's how you will go back. Really interesting. I will write the details, well, not the details, but just what I said on Monday.
Should the equivalences into two slots to give us that projection map over there? Or are they just kind of too random?
Let me see. You're saying should this equivalence,
Yeah.
two equivalences commute with the projection?
With that, for getting that.
Yeah, well, yes, they are going to commute by almost by definition, because the way, I mean, if you have a map from F, so you have a map, isomorphism from S to S prime, that induces you a map, a functor, from F of SG, CG, to F S prime G prime.
Okay, so that's the thing that has to be like cool.
The way that is induced is I take Q to F of Q. And in the central linking system is the same thing. So yeah, it commutes all over, yeah.
So isomorphism means pick an F, and then
Yeah.
the induced maps have it also be X.
Yeah. So yeah, let me repeat that. So an isomorphism is an isomorphism of these two groups that such that the induced functors, the induced two functors, are equivalences, isomorphisms of categories. So it's not just three isomorphisms, it's one isomorphism that induces two others. Well, yeah, it's a good question. Yeah. Okay, I'm going to stop here.